Hi, my name is Steph Gora. I'm here from Toronto, Canada, where I work as an assistant professor in the Department of Civil Engineering at York University. So today I want to talk to you about using innovation and the engineering design process to address drinking water and wastewater challenges. I've drawn much of the material from this for this lecture from a course that I teach, an undergraduate engineering course that I teach at my university. So let's start with a quick introduction to what innovation and the engineering design process are. So to start, what is innovation? Fairly simple definition. It's a new idea, method, or device. So I want to go through a few tools for innovation. Innovation is something that we all have as when we're children, but we can also develop new skills and new methods as adults to help us be more innovative. So the engineering design process is an example of a tool for innovation. It's a deliberate approach to problem solving. It emphasizes finding the real problem rather than jumping to a solution right away. It includes research, stakeholder consultation, and creativity. And most importantly, it is iterative, which means it's more of a cycle than it is a linear process. So there are 6 steps, at least in the way that I teach it, there are 6 steps in the engineering design process. The first is problem finding. This is where we try to identify a problem or an opportunity that we will eventually, as engineers, solve. The next is problem formulation, where we try to understand the underlying problem. This is where we get to that real problem. And then we try to write it out, speak it out, in a very clear and concise form that will allow us to then develop solutions. So the next step is solution development and formulation, where we try to use things like abstraction, creative thinking, to come up with a bunch of different solutions. Then we move on to the next step, which is analysis, where we try to choose between our different solutions and figure out which one is likely to be the most effective, most feasible for the people we are trying to help. Next step is implementation, where we actually implement the solution. And then finally, we evaluate whether or not that solution is working. If it is, great. If it isn't, this is time for us to iterate and go back to the first part of this cycle. All right, I want to go into each of these in a little bit more detail to give you a bit more context about what I'm talking about here. So problem finding, there are all sorts of methods for problem finding. Some of the most effective ones are using things like your own personal experience. When you've experienced a problem in your life or in your work, you'll have a natural understanding of where that problem lies. But not all problems are going to affect you personally, so you may also need to consult with different stakeholders and or observe existing processes or existing, basically problem situations. Now, that problem formulation side is where we move from having these kind of a whole bunch of ideas, sometimes a little bit abstract, again, to having a really clear formulated statement of the problem. So one thing that really helps us with this is trying to understand the present state and the desired state. So the present state is the current situation where that problem exists. The desired state is where we're going to end up after we have solved the problem. So at this point, we are not trying to come up with solutions. We're not trying to figure out what's in between. We're trying to understand where are we starting from and where do we want to end up. Once we understand those really well, we can come up with a well-formulated problem statement that describes the present state and the desired state in clear, concise, and exact language. Now, moving on to solution finding. We don't want to constrain ourselves in the first stages of solution finding. We can use things, once again, like abstraction, which includes kind of thinking big picture, as well as using models and representations to think about the problem state and the desired state, to come up with a bunch of different solutions. Some of these solutions aren't going to go anywhere. That's okay at this stage, right? We're just trying to come up with a lot of solutions. Some of them, you're going to see that eventually a couple to a few of them are starting to stand out as like, this is probably feasible. This is probably going to work out. These are multiple potential ways for me to get from the present state to the desired state. Then we move on to the analysis of potential solutions. This is this is used all the time when you're working in the private sector as an engineer, where you're going to try to understand all those different designs, and then you're going to rate them based on different criteria. So I've used some very common criteria in this particular table, things like the effectiveness of the solution, the acceptability of the solution to, for example, your stakeholders, the public, yourself, The initial cost, often called a capital cost when you're working with infrastructure, and the ongoing cost, again, often listed as the operation and maintenance cost when you're talking about infrastructure. And from that, you score everything according to your criteria, and you will get a total at the end that you can use, a numerical total that you can use to evaluate which of your solutions is most likely to meet as many criteria as possible. So I want to dig into this just a little bit more, again, because it is a really important aspect of engineering. So when we're trying to evaluate our different designs, it's important that we pick out criteria that are relevant to the people who we're trying to solve a problem for, but also that we carefully define our metrics by which we are evaluating our different solutions. So on this slide, you'll see that I have my different criteria, and I also have a series of metrics that tells me what is a good, what would score high, medium, and low for each of these things. Now, this is drawn from an example that I've used in the past about stormwater treatment and trying to develop a stormwater treatment system that would be satisfying and effective. So I've defined effectiveness based on how well that works. So 90%, 50%, or less than 50%. I've looked at acceptability as well. So more than 50% of the population is satisfied, et cetera, et cetera. And you can see that I've got a few different things here. Now, when you're solving a problem, especially the costs probably are not going to be relevant, at least from this example. That's all going to depend on the background research you've done, consultation with stakeholders, and your own, engineering work where you're putting together a design and you are costing out the different elements of it. All right, so once you've gone through that, you have a sense of what your likely best solution is going to be. That's when we move on to that implementation and evaluation. So implementation is literally just, if it comes to infrastructure, building the thing. If it's a kind of another type of solution, maybe a programming solution, it's making it and putting it out in the world. Before we say, okay, we're done, we wipe our hands of this, there's an evaluation stage where we test it out and also usually observe for a period of time to make sure that the solution is solving the problem, that it is in fact moving us from the present state to the desired state. This is a really important stage because this is when we determine whether or not we're going to have to iterate. All right, a couple of other really useful tools for innovation, and these tools are not fully separate from the engineering design process. These are tools that you can use while going through the engineering design process, often at many stages. So one of the most important ones is stakeholder engagement. A stakeholder is basically anyone who has anything to do with the project. I do water projects, so we're often talking about the public, but also ourselves as people who are designing things. We talk a lot about whoever's going to be regulating this, so whatever government department is going to be regulating the infrastructure that we've put together. We talk about the people who are going to be operating it. So if you're building a water treatment plant, you want to talk to the people who are going to have to actually be there day to day and get a sense of whether the design solution that you're putting together is actually going to work for them. There are also sometimes vulnerable groups or specific groups that you will be required to or just should consult with. In Canada, oftentimes this is Indigenous groups who have some claim or some historical management of the land where this project is taking place. Another really important tool for innovation is idea generation. Maybe I shouldn't say one tool, it's multiple tools. So some tools that can help you come up with creative ideas or just generally ideas are drawing on your personal experience, as mentioned previously, consulting with stakeholders, conducting background research, and various creative thinking techniques. So brainstorming is the obvious one. It's something I'm sure you've all done and learned about. Brainwriting is a little bit more deliberate, and it's often been talked about as an alternative for people who maybe don't feel comfortable sharing in a brainstorming session. But the idea is that one person writes down an idea on a paper, and then they pass it to the next person, who either writes down their own idea or builds on the first idea, and so on and so forth. No matter which one of these techniques you're using, it's really important to keep a record. So if you are doing brainstorming, having it all written out on some piece of paper or on a board that you then take a picture of, very, very helpful. With brainwriting, naturally, you're going to have a final document. It's important that you preserve that and circulate it to everyone. So Scamper, which I'm going to describe in a bit more detail on the following slide, is a very defined method for coming up with solutions. And the 5 whys is also one that I find very useful and intuitive. So the example that we use in my course is the example of a monument in Washington, D.C. And if you've never been there, They have a number of historical monuments in the US Capitol. These are generally lit up at night so that people can walk around, and it's very majestic and beautiful. They were finding, though, that one of these monuments was deteriorating quite quickly, and they needed to come up with a solution. Why is it falling apart? Well, we're pressure washing it on the regular. So, once every week or once every 2 weeks. Why do we have to pressure wash it? Well, because there's pigeons, and the pigeons are leaving their droppings, and that's disgusting. Why are there pigeons? Well, there are lots of bugs at this monument, and the pigeons are coming to consume the bugs. Okay, why are the bugs there? Bugs are attracted to light. So the issue was that the monument was lit up during the night, and it was attracting bugs, which was attracting pigeons, which was causing a mess, which was causing the whole the cleaning, which was causing the deterioration. So the solution was to turn off the light later in the evening so that, when there were very few people walking around, and that way we'd have fewer bugs, fewer pigeons, et cetera, et cetera. So I want to go through that scamper method really briefly as well. You'll see that we've got a few letters that are the beginning of these words: substitute, combine, adapt, modify, put to other uses, eliminate, or rearrange. So basically what we're trying to do is open our minds. Oftentimes what we'll do is we'll start with an existing solution, and then try to open our minds to how could we adjust this solution, make it different, again, like rearrange, adapt, and use it to solve our current problem. All right, that's all I really wanted to say about innovation and the design process, at least on an abstract level. But I do want to make it real, and in this case, we are at a course where we're talking about water, wastewater, and waste management. So what I'd like to talk to you about is a project that I worked on as a consulting engineer back in 2010, 2011. And it was in the province of Newfoundland and Labrador in Canada. This is our easternmost province, one of the smaller populations. It's very similar to Sisimiut in terms of if you look at what the communities look like. It's a big rock. There are lots of small communities dispersed around the coasts, and that's a historical situation based on why people came to Newfoundland and Labrador, which was generally to fish. So that's all I really want to say about innovation and the engineering design process. At least that's all I want to say on an abstract level. What I'd like to do now is make it real for you. We're here at a course about water, wastewater, and waste management in small Arctic communities. That's the focus here. So what I'd like to do is tell you about a project that I worked on when I was a consulting engineer that addressed some of these, or involved some of these concepts and these methods. So this project took place in Newfoundland and Labrador, which is a province in Canada. It incorporates an area that is indigenous called Nunatsiavut. So Newfoundland is it's a large landmass, but it has a very small population, and that population is dispersed along the coasts. And that's because the primary industry in Newfoundland historically, but also now, is fishing. So they have lots of little communities dispersed all around the coasts. These small communities, they often lack the kind of water infrastructure that we expect in other parts of Canada. So at any given time, there are usually 150 or more boil water advisories on in these small communities in Newfoundland and Labrador. This is a very large number of communities. It doesn't represent a huge population, but it's a very large number of communities. So some of the reasons for this, it's complex, but boil water advisories tend to be reactive in Newfoundland and Labrador, in part because their water treatment regulations are much more limited than in other parts of Canada. This is reflecting the feasibility of doing this treatment in the province. However, it results in a situation where many communities have, for example, only chlorination for treatment. And this makes them more vulnerable to situations that might result in contamination and boil water advisories. And one of the things you realize very quickly when you go to some of these communities is that the tap water is not of high quality. So that doesn't mean just in the terms of safety. The aesthetic quality is generally bad. So, it's often got a bit of a brownish or yellowish tinge. It can leave stains on clothing and various implements in your home. It has a very strong smell of chlorine often, because in order to deal with all of this stuff that's in the water that consumes chlorine, you have to add a whole bunch before you get the proper amount of disinfection. So there can be a strong odor. And so a lot of times this means that people don't really like their water. at least their tap water. So what this drives them to do is go out, purchase bottled water, and in some communities, people also like to collect water from the land. In some cases, this is a cultural practice, but in other cases, it's just because they don't feel that they have another option. What's really cool about this project is that as the consulting engineer and even as the regulator, that's not where the initial solution came from. This was a ground up initial solution. So people in 7 communities in the province decided to develop decentralized potable water treatment that would be located at some central point in town that would incorporate a pretty advanced technology to treat not a source water, but the treated water that was coming out of their water treatment plant to bring it up to a higher level of safety and aesthetic quality. So the picture here, it just kind of indicates what we're talking about. So the water would come from the standard water supply, go through a centralized water treatment plant. That water would be sent to the homes where it can be used for non-potable uses. But there's also this potable water dispensing unit that's kind of an intermediate situation. This water would be, again, much, much cleaner. And in these initial ones, we didn't know whether or not it'd be safer, but it would be a reasonable assumption that it would be. And then people would collect it in jugs and bring it home and use that for cooking and for just basic drinking. These different systems included 3 that were based on ozonation, so that's an oxidation process. And then there were 4 that were based on reverse osmosis, which is a very, very tight, pressure-driven filter. The aesthetic quality of the finished water was generally very high. It was really nice water. It looked good, smelled good, and they had variable designs in terms of the dispensing system. So I got a couple pictures here. All right. So sometimes they were basically like restaurant style, really nice, advanced looking dispensing systems. It's basically a nice sink, multiple levels to accommodate multiple different jugs and containers. But in other cases, it was much simpler, just a tap coming out of the potable water dispensing unit building. And as I mentioned, they're often located at the community hall or equivalent. So it was somewhere that was central for everyone. Ideally walkable, but a lot of these communities are fairly dispersed, so people would drive, but they didn't have to go out to a water treatment plant to get this water. The company I worked at as a junior engineer, we were hired to take a look at all of these existing ones and kind of get a sense of, you know, what's there, how does it work, do people like it, and how could we build something that could be basically scaled up so that it could go across the province and into multiple communities across the province, ideally addressing some of these water safety concerns that exist in many of these small communities. So some of the important things that we found through this initial review of the systems was that the difference in quality and aesthetic quality between the water that came out of the taps and the water that would come out of the potable water dispensing unit after treatment was one of the factors that would drive whether or not people actually used a lot of water from these systems. So if there wasn't a big difference, people were not that inclined to put in the extra effort to go and get this water. If it was a noticeable major improvement, people were, you know, using it, we think, instead of bottled water and just, making very good use of their system. So the dispensing area was also important. So was it just a pipe coming out of the wall? Or was it something where people felt it was, you know, cleaner, better maintained, or just looked more like a sink? Some people had a lot of concerns, though. These are people in the community that our company talked to. These mostly related to cost, both the initial capital costs and ongoing operational and maintenance costs. And they also worried that their community might not have those resources in-house to operate or maintain the system. So what we did as a company is we took all of this feedback, as well as information about those existing systems, as well as our knowledge as engineers of water treatment technology. And we came up with a system that we were pretty sure would give very high quality water and that could be easily scaled up. So I've got a little schematic here showing the basics. I won't go through it in a lot of detail, but basically we combined the 2 processes that people were already using, ozonation and reverse osmosis. We also added an interim storage tank so that we could treat the water, you know, at any time of day, have it stored, and then people could take as much as they needed. They didn't want to have to, you know, have a really, really small flow rate coming out of there. And we added UV disinfection at the outlet so that the stored water would get that extra little hit of disinfection just in case something was growing in the storage tank. So this was implemented. At this point, we have about 32 communities who have the new potable water dispensing unit. 10 of those 32 are Indigenous communities in Labrador. The water quality is very good. The nice thing about, one of the many nice things about the Newfoundland government is that they maintain all of their water quality results in a very easy to access format on their website. So you can go in and see that the potable water dispensing units are regularly achieving water that is well above the requirements in that province and is in line with the federal recommendations for water quality provided by Health Canada. There are, however, ongoing concerns. A lot of this is related, again, to cost. People were correct in their concerns. These systems are expensive. When they were first rolled out in 2012 or 2013, the cost to build one was about $300,000, which seems very small compared to the budgets that we see in larger systems, but is quite substantial for a community of 200 people. And also maintaining these systems is difficult. So you have to have somebody who has the skills to do it, but this is not going to be their full-time job. So you have to make sure that you're able to pay them correctly and have them stay in the community and not be too busy with other things that they can't actually, take care of this thing. The government has come up with some solutions to this, whether it be subsidies or there's a lot of operator support. Again, I won't get into detail about that, but I'm always happy to talk about it. One of the special concerns that's come out recently is that during the COVID-19 pandemic, there were very specific requirements for the people who operated the potable water dispensing units to keep them very clean. So all the sanitation, all the masking, all of that. And that turned out to be very challenging. That added a whole other layer of complexity and a lot more labor to these people's jobs. And that was very challenging. Very cool paper talking about this shown here. All right, now on the positive side, the water is great. And this has driven a change in the way that people use water in some communities. This is a wonderful study by Wright et al. And they looked at before and after a potable water dispensing unit was installed in an Indigenous community in Labrador and talked to people about, and they didn't talk to them in hindsight, they communicated during the process, what kind of water do you like to use? And so initially, a lot of people were purchasing their primary drinking water, so the water they were using for drinking and cooking. And after the potable water dispensing unit was installed, this proportion went down substantially. That means that people were not needing to spend as much of their money on water as they had previously. So this is very helpful for people living in these communities. All right, so that's my example. That's my talk. Thank you so much for your attention. I've left a few links here for you if you'd like to learn more about any of these items. And I'm also very happy to talk to you at any point. Please just send me an email. This is stuff I'm really excited about, and I'm just so happy to be able to share it with you today.